Here we are once again. It is the physics video lecture, psci 168, video lecture 12. Got some great stuff today. We're talking about satellite orbits. I'm going to review that whole subject. I'll work the problem that I had given as a homework assignment, and some of you may have already tried it on your own. Set it up. Just want to make all the points, and then we're going to talk about Newton's laws, and we'll gain a huge piece of our energy puzzle from this discussion here. But we're doing the satellites just because we can, right? It's a very interesting topic. We learned about free fall, and then I said, well, if you have free fall on the horizontal throw, you have satellite motion. So we're talking about satellites that are in near Earth orbit. In near Earth orbit. And there are some requirements for that. First of all, we have to be above the atmosphere. There can be no friction, right? It has to be true free fall. So above atmosphere, and then the orbit is going to be a circular orbit, and the plane of orbit has to contain the center of the Earth as well. So you can't have an orbit that's like a halo. And you know, if you had our Earth here, you could not have a satellite orbit like that. It's not going to happen. It has to go around the Earth such that the plane of the orbit contains the center of the Earth. I'll go ahead and write that. Circular orbit, orbital plane contains center of the Earth. And what we're dealing with is free fall. So free fall is a fall without friction, and the question is, why is a satellite in free fall, an orbiting satellite? But because we have free fall, we can consider the horizontal throw. This is something that a pitcher in baseball could do. Just throw a ball horizontally. And when you throw a ball horizontally, here's an X and here's a Y axis. If you launch it from height H horizontally, it's just going to move forward and fall at the same time. So we've got that horizontal throw, and what we have is, I'm going to call this distance that it goes L. We have L is equal to V0t, and the height, and y is equal to the height minus 1/2 gt squared. We're not actually going to have to do any particular calculation with these, but when I did that projectile cart demonstration where the cart kicks the ball up and catches it, that was the proof of these two statements, that they're independent of each other. Now the thing about this independence means that if I throw it with twice the initial speed, it's going to go twice as far. So I'm going to show a couple of different speeds. So this would be a slower throw. This would be a faster one. This would be yet faster. How far it goes is independent of what it's doing in the vertical direction. It has a certain time to land, and if you throw it twice as hard, it goes twice as far. And there's even an interesting picture in a book by Isaac Newton, so hundreds of years old, in which he makes this exact argument. he draws an Earth with a cannon on top of a mountain, and then he does precisely these trajectories. I'll exaggerate the mountain a little bit, okay? And he does precisely these trajectories. He says, well, a low initial speed, faster, even faster, is going to keep going further around the Earth, but if I have the adequate speed, let's do that one in red. If I have adequate initial speed, it's just going to keep going. Okay, you guys make a better picture. It's going to keep going all the way around. So it's falling the whole time, but it has so much speed that the curvature of its path matches the curvature of the Earth. So that's a pretty amazing fact. This is our Earth, so we say it has a radius of Earth. This here, we can draw a little better. Okay. But that's the idea. So this idea goes back hundreds of years. So once you understand this, then for a near-Earth orbit, we just have to do that construction I did at the last lecture. But I just wanted to reiterate all of this. And any words of wisdom you can add to this in your notes, feel free. These trajectories are with progressively faster initial speeds. Eventually, you find the exact speed that will go around the Earth. And that's what we're going to do now. So now we come to our construction from last time. And so make a nice large circle. We're launching horizontally, okay? That's the center of the circle. So we're launching horizontally, and of course the actual path is skimming the surface of the Earth here. And because we're near the surface of Earth, we know the acceleration is just 9.8 meters per second squared. If we were much further away, the acceleration changes according to the law of gravity. We're not going to go there though. If we're near the surface of Earth, we've got that 9.8 meters per second squared. And so I label this L. This little bit here is my H. This is the radius. Of course, this is also the radius of Earth from there to there. So I have my, so it's labeled as H equals fall in 1 second, distance fallen in 1 second equals 1/2 gt squared, 1/2 9.8 meters per second squared times 1 second. Quantity squared, seconds squared cancel, 9.8 divided by 2 equals 4.9 meters. So that's what H is. R is equal to 6.38 times 10 to the 6 meters. That's the value that we measured together, so to speak, in this class. And L is what we want to find, because our projectile is going to go L forward in the same time it falls H down, same time it falls 4.9 meters. Since that's 1 second, right, in 1 second, then L divided by 1 second will be our speed in meters per second. So here we go. We have Pythagorean theorem, r squared plus L squared equals R plus H quantity squared. So we'll do a little bit of algebra. R squared plus L squared equals R squared plus 2RH plus H squared. When we expand that out, R squareds we can drop from both sides. L is now equal to the square root of what's left. And what's left is 2RH plus H squared. Now, I'm going to put an approximate sign here, but this answer is actually an exact one. Turns out we can drop the H squared compared to the h term here. Because h is 4.9 meters, and the r here that we're comparing to the other power of h in there is 6 million meters. Okay? So we're looking several decimal points down, and so we can just do 2RH. It's a very good approximation. Actually, this expression is exact in the correct theory, in the more sophisticated theory. There's nothing incorrect about what I'm doing, by the way. Okay, so 2RH, and then if you got this far, if you plugged everything in here, of course you had some numbers that you discovered this was very tiny, but 2 times 6.38 times 10 to the 6 meters times 4.9 meters, you take the square root of that, and you approximately get 7,900 meters. Okay, that's approximately close enough for us, and because of that, we're going to say it's that many meters per second, because this h was falling in 1 second. Okay, so our orbital speed is 7,900 meters per second. So v orbit, we're just going to write 7,900 meters per second. And if you think about it, that is very fast. Okay. That's roughly 5 miles. If you think in miles, that's roughly 5 miles every time you say 1,001, 1,002. 5 miles each time. Okay. So we found the orbital speed, and because it's so large, it's going to be of interest to us later on as well. We have applications for this orbital speed. I want to talk about satellites a bit more. Now that we have this, right, we have the conditions, we have the horizontal throw, baseball, etc., etc. There's the speed we found out with. Here's the construction. I actually always assign this as a problem on my exams. I don't know what we're going to do this year, but in the past I've always assigned it as a problem, and people would actually just memorize is the wrong word. You actually have to learn this so you can repeat it, and you see the pieces there, various pieces, and then this calculation with the Pythagorean theorem. Okay. But we've done everything in this calculation so far. We talked about how big the Earth is. We talked about free fall. We talked about geometry, proved the Pythagorean theorem. So, I want to drive the point home that as far as we can go, we want everything that we do in this class to have been shown, demonstrated, and understood by us together. Okay, so let's talk a bit more about satellites. I'd like to show a lot of slides of satellites, and it used to be a really nice program I could demonstrate in class. I'm going to have that something that you guys do. Okay, you want to look up some nice pictures. Actually, you'll even find this one online if you want to print it out. I mean, if you search for this, Newton satellite orbits, you'll probably find his original picture. But yeah, let's continue for a bit. This picture is too good to erase. Okay, continuing with the satellite orbits, we now have the orbit, and I'll just get a small mock-up of that picture again. So radius Earth, V orbit equals 7,900 meters per second, roughly. So the question is, how long does it take to go around the Earth once? And that time is called the period of the orbit. We'll use capital T for it. Use capital T, and how long is that? hours, minutes, seconds, days? Well, we will do this. We know that speed is equal distance divided by time. Okay, that much we know. Now the distance to go around the Earth once is the circumference of the Earth, 2 pi radius. Okay, and the time I just defined as t. So we will solve for this just with one algebraic step or two, and what we find is 2 pi r divided by v. Now we do so much of this that make sure you take enough time to recognize how I got from here to here and practice that. Okay, practice those little algebraic steps, and it's one of the main things we do in this class is express the relationship as an equation and then find one of the expressions isolated. So here we isolated the time. You would plug in 2 pi times 6.38 times 10 to the 6 meters divided by 7,900 meters per second. The meters are going to cancel and the seconds are going to come up to the numerator. Your answer is going to be in seconds, somewhere around 5,000. Look that up and convert it to hours and minutes. I'm just going to write approximately 1.4 hours if memory serves. But this is homework for you guys. As you're working your notes, make sure you have a calculator at hand and go ahead and do this and find out how many seconds and then how many hours. Okay, 3,600 seconds per hour, but you can figure all those things out. But yeah, the period of orbit is not that, doesn't take that long. And so the astronauts in near Earth orbit, space shuttles and things like that, International Space Station, they're going around every 1.5 hours. And all the while the Earth is rotating underneath them. So it's a pretty interesting thing. Good, so that's from the speed right here, orbital speed, to the period of the orbit right here. So let me also then state right here in terms of homework, we want some images of satellites and satellite orbits. I'll put a little bit of a list of what I'd like you to find and what I want to teach you guys about. So satellites, what we've talked about now are the near Earth orbits. Okay, near Earth. And let's have a picture to go with this. So if you've got a satellite orbiting our Earth, the orbital radius we're going to call little r. So there's a near Earth orbit. So near Earth, little r is approximately equal to the radius of Earth because we're just a little bit above the surface. And then we had the orbit is equal to 7,900 meters per second, and t is approximately 1.4 hours. Okay, by this time you've found the number and put it in there if you want, okay? So this is one kind of satellite. There are many others. And yeah, let me discuss these first. The interesting one that we want to talk about now is geostationary. Now we have not and cannot calculate the geostationary orbital parameters with what we've done here, but we can understand them. Gravity is getting weaker the further away we get from the Earth, and the orbital period is increasing And the geostationary orbit has a period of exactly 24 hours. Not 1.4 hours, 24 hours. And that's significant because the Earth rotates about its axis once every 24 hours, right? That's a day. And because of that, if you have a satellite in orbit about the equator, the geostationary orbit, it will always be above the same spot on Earth. So as the Earth orbits, the satellite orbits with it. Okay. So the geostationary orbit is very important, and I'll just give you a bit of a sketch on how that is. So suppose the Earth is rotating. This indicates the rotation of the Earth. Our geostationary satellite is out 5.5, 6. I'd have to look it up again. But if that's a satellite, that's the rough scale of the distance from the Earth. Okay? And it would be orbiting, in a large circle like that. So geostationary orbit, certain weather satellites, it's always above the same spot on Earth. If you have a satellite dish, it's pointing somewhat south, and it's actually pointing at a geostationary satellite, very far away. Okay? We're looking at 5 Earth radii. And then there are smaller orbits, there are larger orbits. They don't, they go every which way. Now, I used to be able to show the JTRAC program I mentioned last time. JTRAC, NASA, and you may still, last time I looked, that program is no longer working, but you may still find images online. So in terms of the homework here, for your notes, see if you can find some good relevant imagery and print it out and put it in your notes. Okay. Satellites, orbits, etc. Images. So you want something nice for your book. Like I said, that Newton picture there. I have a bunch of slides that I used to show. But it's a major chapter we just did. We calculated the speed fair and square. We understand about satellites now. There's another satellite orbiting the Earth called the Moon. And it is far enough away that it takes about 27 days to orbit the Earth, okay? Because gravity is weaker out there. But there are hundreds, literally maybe even thousands of man-made satellites orbiting the Earth. Definitely hundreds orbiting the Earth in near-Earth orbits, and there are many out here in the geostationary orbit. What else would you guys know? Yeah, you could look up what weather satellites are doing. GPS. I should put a special note there. Everybody has knowledge of GPS. That stands for Global Positioning System, and it's actually a network of satellites. All of your GPS devices in your car and so forth are in contact with 3 satellites at the same time, which is how your location on Earth is determined. So yeah, GPS is an interesting thing you might look into as well. Global Positioning System. Okay, good. Very important chapter here. Let's see what we're doing time-wise. Okay. And what we're going to make use of, like I said, in the future, this particular speed is going to be of interest to us because it represents a speed of objects in our solar system. In other words, this is the magnitude of the speeds of things that are zooming around our solar system, and including zooming around our Earth. Okay. So we'll come back to that. Right now, I want to move into Newton's laws of motion. I'll set this up here. So I said we had to study motion in order to fully understand energy. And because satellites are such a good topic, I decided to, bring them into the mix as well. But next we'll talk about Newton's laws of motion. And then we'll be able to return to the energy concept. So the next topic here is force and motion. Newton's laws. Formulated in the late 1600s, a long time ago. Okay, there are three important laws. The first one I'm just going to, because I'm doing this quickly. First one is the law of inertia. Objects, a force-free object remains in its state of uniform motion. Just for the record, okay? An object without force on it, a force-free object retains its state of uniform motion. The key here thing is inertia. This is the tendency of an object to stay put, and if it's moving, to keep moving. Okay. The second law, and this is the one that I'm after right now, is that the net force on an object is equal to its mass times its acceleration. So we haven't had mass yet, but actually mass, the reason we have the first law here to talk about is mass is a measure of inertia. Okay. The measure of inertia is called mass. Okay. So this here, the second law, is the one that we are going to showcase. It's actually really rich if we were a physics class, and we are a physics class, but if we were another physics class, we'd spend a lot more time on this. But I can point a couple things out. We already know about force. Weight is a force, right? Force is a vector. I draw the arrow on top. Force is a vector. Forces add like arrows. When I say the net force, I mean the sum of all the forces, the vector sum, the sum of all the arrows. And we actually have some experience with this, okay? The directionality of force. I talked a lot about it. It's equal to the mass times the acceleration. Well, the acceleration's a vector, although we've talked about it in one direction primarily. And everything we've learned about motion culminated in the acceleration, namely the acceleration of free fall. So we know something about that, but the mass is this proportionality constant. It's a measure of the amount of matter. So here's well, these are all three masses, right? I have a mass of water, a mass of metal, and another chunk of metal. And as a weight, it's about 10 newtons. I should check, right? It's about 10 newtons, good. And a liter of water is always going to be about 10 newtons for you. And then this chunk of metal here is also about 10 newtons. But this chunk of metal now is referred to as a kilogram. Okay. Measure of inertia is called mass. And the unit of mass, square bracket, kg, kilogram. Now, is there a difference between weight and mass? That's what we're going to get at here with Newton's second law. Before I do that, I'll just put the third law down as well. It's called the law of interaction. You've also heard maybe action equals reaction, action, reaction. It means that if one object exerts a force on a second object, the second object exerts that same force back on the first object, minus sign in front, same magnitude, opposite direction. Okay. So those are Newton's three laws. We want to talk about this one right here. Okay. So again, net force equals mass times acceleration. The forces we know are weights primarily, and the acceleration we know is the acceleration due to gravity. So I'm all set up to make my next point. Okay. So I'll put that as a note here. Weight is a force. Tension, like the tension in a string we learned, is also a force. So that's the forces, and G is the acceleration we've learned about. Acceleration due to gravity, that's what we say. And we know that that is our free fall. Okay. So we know about the ingredients to Newton's law. Now we're going to tease out the discussion of the mass here. Now, to discover this law, we don't really have time. Okay, we have to say Newton's a genius, had a lot of good reasons for it, but we're just going to take that as a fact. Okay, Newton's law of motion. Yeah, I should actually work on proving Newton, or deriving, generating Newton's law for this class as well, maybe next time. Okay. So good, Newton's law of motion, and what we're going to do now is, so next, this is a demonstration mostly in our mind, but we'll pay close attention to it. So imagine I have the scale here, old 10 Newton weight, okay, and imagine I have this tied with a string. So I've got a little string in between here. Same scenario, okay, 10 Newtons, there's my weight. So that's what I'm going to draw. And this is what we're going to call our demonstration. So we have scale, we have 10 Newtons, there's the hook, there's the string, there's the other hook, there's our mass, 10 Newton weight. Okay. This is the demonstration. And the forces, we say weight is a force, and then we say tension is a force. Okay, it makes total sense. Tension in the string, 10 Newtons, weight 10 Newtons, equal and opposite, net force is 0 to things not moving. So that's my first picture. Now my second picture is when I cut the string. Okay. So we're going to cut the string, and we're going to draw the same picture. Now if I cut the string, I have this thing. There's the string, right? The scale now reads 0 for what it's worth, because this thing is falling, and it still has its weight. Okay. So after I cut the string, object is in free fall, and we've studied free fall. Objects in free fall, of course, the tension in the string is now 0 instead of 10 Newtons. So here's what we have. We have this object here, I'll just indicate with these lines that it's in free fall, and it has the weight on it. So let's look at let's look at Newton's law here. F equals mass times acceleration. That's generally, in this particular case, and here we have weight, because that's the only remaining force, it's the weight, is equal to m times the acceleration due to gravity. Okay, see what I did? I have this, I have mass, and the acceleration due to gravity. And this is what we just learned now. This is what weight is. Weight is mass times the acceleration due to gravity. Very, very important result. So I'll write it here again. Weight equals m times g. Mass times the acceleration due to gravity. And so from here on out, that's what we're going to use. We're always going to write mg. I never have to write weight again. Okay, I write mg for an object. If I have an object like this, I write m times g. So from here on out, we know that weight is mass times acceleration of gravity, so they are not the same thing. This object here is a 1 kilogram object. It's an object of mass 1 kilogram. Then multiplied by 9.8 meters per second squared. So let's put that as an example. But I just had that word kilogram. I'm going to continue right under here. Leave that there for now. So the example, 1 kilogram times 9.8 meters per second squared. So that's 9.8 newtons. Okay, I always was saying 10, very, very close, right? 9.8 newtons. So weight and mass are not the same thing at all, because if you go to the moon, this g number is now about 1.6, not 9.8. So the weight on the moon of this object, we took this very scale to the moon, and here we've got our 10 newtons, or 9.8. On the moon, it would weigh about 1.5 newtons, 1.6 or so. Yet it would be it would still be the same chunk of metal with all the properties. You could damage something with it. It's still as hard as it was before. It has the same number of atoms, all those properties, but it weighs less. So the difference between force and weight is very important. So force is not equal to, or weight is not equal to mass. Okay. Mass is not the same thing as weight. So you have the weight, you need gravity. Okay. So once again, 1 kilogram of water, that's a liter of water. You put it on the scale, you get your 9.8 newtons. Okay, so we have that. Let's see how we're doing time-wise. I'm just going to wrap this up. This is a good because now I can say next time with the mass, we're going to be able to get back to the energy. Okay. But I want a little more time for that. So this is a good place to stop. We have the next time motion. So we already have force and motion, right? As Newton's laws, we're going to have motion and energy. So that's our next topic. We'll recapitulate this briefly. This is such an important thing, and then we'll move on to motion and energy That's excellent. Okay, good. Everybody, keep the great notes coming in. Very nice. Also, do fill in any of the stuff I mentioned in class here. Type it in your calculator. And once again, these algebraic steps that I do, the whole purpose of this is you write them down, but you have to go back to your notes and practice those steps so that you can actually do them yourself. And then we also want some nice images of the satellite, of the entire satellite theme. And we'll be well on our way. Good. See you guys next time.